everyone. So I'd like to review the term work a bit, and then we are going to discuss how to calculate work in different cases. So the work is, first of all, how we defined is that it is a way to add or subtract energy from the system, right? So the unit, so first of all, the symbol is W, so please do not confuse this with the weight force. And I would suggest to check the units, dimensions, has a unit of, since it is a way of kind of adding or subtracting energy, you should kind of think that the unit should be the same as the energy, right? So the units that we use is joules, okay? In terms of the dimensions, I want you to also realize that joules is also Newton's meters, okay? We don't really use Newton meters for joules, although they are the same dimensions. For the work term, we do use joules more than Newton's meters, but if you just leave it as Newton meters, it wouldn't be wrong either, okay? Later on, we will be using Newton meters for something else, so it's nice to use joules so that you can relate to energy better that way. So again, the work term is in the energy conservation equation, right? So we put all the energy terms on the left side, and we will discuss this equation in deeper in the next chapter, and the work term is on the right side. So this is what we're talking about. And for the problems, when you're doing solving problems, if they're asking you to find the work done by, maybe the weight force, normal force, tension force, spring force, or any kind of forces, the first thing you do is draw free body diagram to figure out the work term, okay? And see how many forces acting on the object, and then you're gonna split that many pieces in the work term. So you're gonna write down what the work term is: work done by the first force, work done by the second one, work done by the third one, maybe you have a lot more, and work done by the nth force. So this kind of assumes n number of forces, okay? So you are going to write this down individually. When you write this, the work terms for each forces, you need to think about how to calculate them. Are they constant? Are they variable? Do I know what they are? So that kind of brings us to the next step. Okay, so if another thing that can be given is maybe you are given a graph. So there are several multiple choice questions, quiz questions. So again, if you can go back, if they were not clear, you can just check again. But if the plot is given, and the plot is gonna be the force versus distance, okay, and assuming there's more than one dimension, this is going to be maybe like fx versus x, okay? So it's going to be consistent. How do we calculate work in that case if we are given that plot? It is the area under the curve, okay? So you just look at the area under the curve. Just be careful if it is below the distance axis, then it's going to be negative, because the force values will take negative values. And again, just check the values of force and distance, if they could be positive or negative, and that will affect the work sign. Work is scalar, okay? So let's just add that in here. So it doesn't have a direction, and it's again kind of some sort of energy given or taken from the system. So it only has a number and has a sign as well, but that sign is really related to, is it given or is it taken? So you kind of think about that way, but it doesn't mean it has a direction, and it doesn't have a direction, okay? That's really important as well. So work done by constant force is again, when you, especially later on, we will be using the energy conservation a lot, and once you figure out how many forces acting on the object, and then you're writing the work term in this form, here. So you're individually thinking what type of force you have. And you should ask yourself, am I dealing with a constant force or a variable force? Or do I know what type of force it is, okay? So if you are dealing with a constant force, like weight force, right? And most of the time, normal forces are also constant, but not necessarily. So you have to check and figure it out. So if you're sure that you're dealing with a constant force, then what you do is just simply do F dot D. Okay, and this can be written as Fd cosine theta. Again, this F could be the weight force. Distance is then the kind of the height, or maybe another displacement the object is going through. Then find the angle between that force and the displacement, and that's your theta. And if theta is less than 90 degrees, then you're gonna get a positive work done. So that means like you're adding energy to the system. That force is adding energy to the system. If this angle is between 90 and above 90 and up to like 180, it's going to be, for example, negative. So you're going to kind of check and see if you are what is the direction, what is not direction, what is the sign of the work done, is it added energy or taken energy from the system by that force, okay? And then you're gonna write down maybe later for the energy conservation equations, you're gonna put that piece into the kind of the big puzzle. So that is the constant force. So you can only use this equation here if F is constant, okay? What do we do if it is variable force? Again, hopefully you checked the notes and you already seen the equation for this. But first thing we need to kind of understand is that we need to do the integral, right? So if it is variable, you're not using this equation. Instead, you're kind of thinking about the integral and thinking about the components. Fx dx is one of the integral, and plus it could also have y component, so fy dy, and maybe z component as well. Okay, so you have all of these. Since the integrals are over distance, so for example, this would be x initial to x final, this would be y initial to y final, and this would be z initial to z final. Okay, so because your differentials are x, y, and z, okay? So you're integrating over these. And again, some problems, most problems actually, the object is not going to go through three-dimensional displacement. So maybe it has only moving along x direction, so then you're going to keep the first term only. Maybe it has like 2 dimensions, then you're going to keep the first 2 or something. But this is the way to find the work done if you're dealing with a variable force. In these cases, they're going to give you the force not as a number, so it's not going to be just a constant value. It's going to maybe depend on x or y or z or all of them or some of them, okay? Again, there's an example problem that I added. It's 7.31. If you haven't checked that video, you can watch it, or there's also PDF form. You can also check the solution to see how this is done, okay? And that was just a one-dimensional case, so we just really focused on this part of the equation. And this is again done for any variable force, okay? So you can really apply it and find out as long as you have the function of F in terms of X, Y, or Z. Next is a specific case. So this is really a specific case of that variable force. So it's an example of that. Spring force is a variable force because F is in magnitude, it is k times x, and k is the spring constant, so we are going to put s here. This is the spring force. K is the so this is the spring force. K is the spring constant, and x is the stretch or compress. Okay. So that is kind of the displacement. Okay, so like it's in meters. So from the unit for K, if you wanna get that, you see that it is Fs over, first of all, X, right? So the unit is gonna be in newtons divided by meters. So if you see a number, a constant given in newtons per meters, it's usually the spring constant. Okay, so it is related to the stiffness of the spring. So you could have a physical spring, right? It's like bent wire kind of. You can like see it that way, and then how stiff it is really related to this spring constant K. Or it's really anything is like behaves like a spring. If you have a plastic plate, let's say, if you just fold on one side and then let it go, it acts like a spring as well. Okay, so it doesn't really look like a curled wire. Many other materials act like a spring force. Act like a spring. Okay, so in the notes have the calculations, but since spring force depends on x, so it is not just a number. K is a value number, it's a scalar quantity, but x is not. So what happens then is this is a variable force. So when you find out the work done by the spring force, you would use the work done definition for the variable force to get the equation. So the notes gives you kind of follows. If you follow the notes, you will find out what the how to get there. But I'm just gonna show. I'm gonna show how to get the. If I click on the right thing. Okay, so this is the work done by the spring force, Ws, and from the integration of Fs dx, okay? And again, cosine theta. If you are just using Kx, then you need to take cosine 180 because the displacement and the force, they always opposite to each other in a spring force. So if you're stretching the spring, the force is opposite direction than your stretch direction, okay? And so to introduce that negative sign, either you can take that Fs to be negative Kx, or if you're ignoring the negative sign in the equation, in the function of Fs, then you need to put 180 degrees for theta to show that difference between F and X. Okay, so starting from here again, you get an equation, and in the example problem I also showed how to get that. So I'm gonna skip that part, but this will give you 1/2 K X initial square minus 1/2 K X final square. Okay, so that is the work done by the spring force. Again, this is you can get this equation from this, but in the exam or so, if you know that it's a spring force, you do not need to show that because this is already given to you. I just want you to get familiar with how to use this. Okay, be careful with one thing, especially next chapter. I already showed that in the example problem 731, but we are going to relate this to the potential energy, the change in potential energy of the spring, or elastic potential energy. Actually, we're going to call this elastic potential energy. So it's change in elastic potential. This is in chapter 8, okay, but I did kind of briefly talked about it in the example problem. So there is a relation between them. If you realize what we're doing so far with energy conservation, with the weight force, we either put it on the work term on the right side. I put it over here, as this is the equation here. We either put the work term on the right side as one of the work terms here, or we and ignore delta U, or we do the opposite. So we keep it as delta U and ignore the weight term, work done by the weight term. So you have the you will have the same option here. Either you can use the spring force as the work done on the right side in the work term, or ignore it and then keep it as the change in potential energy, but it's the elastic potential energy. And since you're putting on the left side in the form of potential energy, when you do that, this is the final minus initial, and potential energy will be defined as 1/2 kx squared. So if you look at it, this form, I just want you to compare these two. This is 1/2 kx squared divided by minus 1/2 k initial x squared. So realize one thing, this is initial minus final, this is final minus initial. And this happens because, again, if you keep it in the work term, you're putting it on the right side in the energy conservation. And if you take that term on the left side, things are gonna switch, right? The signs are gonna swap. And that, if you rearrange it, then it becomes x final becomes positive, x initial becomes negative. So kind of be careful with this. This more is coming up, but this is going to be the challenging part, and I want to give you just a heads up on this. Okay. I think this is the main things that I wanted to cover for today's review.